So it's my great honor and pleasure to introduce our speaker today, Dr. Dion Antao. Dion is an assistant professor in the 𝗔𝗰𝗵𝗶𝗃𝗀𝗃 66 faculty fellow in the 𝗔𝗰𝗵𝗶𝗃𝗃 66 Department of Mechanical Engineering at the Texas A&M University. Dion received his Bachelor of Technology with honors from National Institute of Technology, 𝗘𝗳𝗃𝗃𝗃𝗃 in Mechanical Engineering. He received his master's and PhD from Drexel University, working with Professor 𝗘𝗂𝗃𝗃𝗃𝗃. Before he joined Texas A&M, he completed his postdoctoral research at MIT, working with Professor Evelyn Wang. Now he's directing the Thermal Engineering Group at the Texas A&M. His research covers two-phase flow and heat transfer, solid liquid vapor interfacial phenomena and surface chemistry, plasma physics and engineering, and cryogenic refrigeration technologies. His research is supported by ACSPRF, 𝗘𝗂𝗃𝗃𝗃, EERE, NSF, and industry sponsors. To me, Dion is a friend, a mentor, and a legend. Many of the times, when researchers get together, we'll need someone to throw in a question or a thought to break the ice and ignite discussions. And that someone during my PhD turned out to be Dion. So there was a time during a seminar after the speaker concluded discussions, no one asked any question. Everyone was waiting for Dion. And then someone asked, "Where's Dion?" And someone else responded, "He's on travel." All right, then we needed to rely on others. That's how important Dion is to me and to our others. Thank you. Dion, the floor is yours.
Thank you, Han, very much for that introduction and your kind words. Let's see. Okay. Good morning, good afternoon, and good evening to everyone, depending on which side of the world you are in. Thank you for the invitation to present to this group, our thermal transport community. As Han said, my name is Dion Antao, and I'll be talking a little bit about what our group does today. The main part of the talk will be related to my work, our work in our group on condensation heat transfer. Starting out, I'd like to give a little bit of an overview of myself and what we do. And the reason I want to do that is because, as you'll see, some of what we do is all over the place. So I did my master's at Drexel in plasma physics and engineering, my PhD in thermoacoustic cryogenic refrigeration, and then my postdoc was in liquid vapor phase change heat transfer, which has resulted in this melting pot of research interests at the fundamental level in phase change, mainly liquid vapor phase change heat transfer, looking at surface chemistry and interfacial phenomena, and some plasma physics, plasma chemistry, and some plasma material interaction chemistry. And what I've tried to do is use what I've been fortunate enough to have training in these diverse areas and mix and match in order to enhance applied technology applications in the area of thermal management, enhanced condensers, plasma modification of materials, some nascent work in development of metrology techniques for non-contact measurements, and some very new work on enhanced separations with some plasma-based separations for extraction of rare earth elements and critical materials such as lithium and cobalt from produced oil and gas waters. This is a basic overview of the research teams in our group. I'll be focusing today's talk on the interfacial interactions and surface engineering work related to condensation. And I'll briefly go over some of our work on thermal management and plasma physics and engineering. The video that you see on the bottom right here is some of our latest work where we are using these non-thermal plasmas. Non-thermal in plasmas is a bit of a contradictory term. It's non-thermal because it's low temperature compared to the temperature of really high temperature sources such as the sun, which are thermal plasmas. Temperatures here are still high. From this perspective of the thermal transport community, you're looking at temperatures between, I'd say, about 400 to about 1,000 Kelvin, anywhere in that range. The plasma that you're looking at here is probably in the 500 to 600 Kelvin range. And we are using it, and with what we have seen recently, I won't discuss that in detail, but we've seen some ability to treat oil and gas produced waters to extract some cobalt, a bunch of lithium in fairly stable forms. And as always, I wanted to highlight my students at the start of the talk. They are the ones who do all the work. I get to come up with interesting ideas along with them, and then they have to go and execute whatever we discuss. And so I'd really like to highlight them and their efforts. I got 3 slides coming up, which are basic overviews of some research projects that are ongoing at the moment. And then I'll go into the bulk of the talk. The first is ARPA-E funded project through the ASCEND program, where we are developing next generation all-electric motors. And these are high power density motors, at least 1.5 to 2 times the power density of commercially available motors. At the moment, it's led by the professor in electrical engineering, 𝗗𝗂𝗃𝗃𝗃, and it's, as you can see, it's a fairly large team. We are 9 faculty, 8 of us at A&M, 1 at UT Dallas, 3 of the folks working on electrical design of this motor, 1 at A&M working on structural aspects. We've got nominally 4 people working on thermal aspects, including the controls of the thermal system, and then development of these polymer nanocomposite materials as high dielectric strength and ultra thin materials which have high thermal conductivity. What you see at the bottom left of this slide is a mock-up of what the motor looks like. I didn't put a scale bar here intentionally because the design is still in flux to a certain extent. We just got into phase 2 of this project, and so we have to actually build this full scale motor. It's roughly, I would say, about 1 foot in radius at the most, and it can produce power on the order of about 250 kilowatt, which is required for flight, at least takeoff conditions. The key aspects of this motor to achieve this extremely high power density of 13.2 kilowatts per kilogram is this co-design of the electromagnetic, thermal, and structural components. The motor itself is a dual rotor axial flux motor with the Hallback array of your magnets. It helps the motor increase the efficiency, as well as along with the materials that are used in the stator and winding components, and it keeps the motor dense and small in terms of a volumetric density too. We have some co-design of thermal aspects. We've not over-designed the thermal system to be capable of hitting the takeoff conditions, which is the maximum power conditions. We do have a thermal energy storage component there that helps with the transients during takeoff. And so that helped us to sort of design a less stringent system for the liquid cooling aspects. And finally, we have a control system that, depending on whether we are operating in 2-phase or single-phase flow, we might have to activate. Overall, some key components of the system that I've not mentioned include the lightweight, high thermal conductivity dielectric insulation, and this is a polymer nanocomposite we've achieved. Professor Jamie Grunland's leading that effort, and we've achieved, I believe, thermal conductivity is on the order of about 0.8 to 0.9 watt per meter Kelvin of this polymer nanocomposite, with the goal to be reaching about between 1 and 2 watt per meter Kelvin. The second aspect or second project that we have ongoing, it's recently wrapped up, is funded by EERE. But to help you understand what the project's about, I want you to take a look at this video. We have 2 electrodes. sitting in a saline solution. So just in this case, it's just salt water. It's tap water with a little bit of common table salt added to it. We're going to be generating a plasma between these two electrodes. Keep in mind the actual plasma is it's a pulse plasma. It's about 40 to 80 joules in this case. I forget which exactly. It's either 40 or 80. And it's generated very rapidly within 10 microseconds. It's not the fastest we can generate, but for this energy, it is close to the fastest we can generate. Think about this as lightning underwater. Lightning's accompanied by thunder. And so what you will see is this formation of the plasma, and accompanied with that initial plasma singularity, there is a bunch of shock waves that go out. The shock waves have extremely high pressures. You form this bubble, and the bubble collapses. You have this cavitation singularity, and each time you have that singularity, another shock wave is generated with high pressure, and that bubble constantly oscillates, but I'm just showing you the first cycle. So think about this, that pressure wave that's generated is so high that it is about 10 times it's on the order of about 1 to 2 gigapascals. That's at least 10 times the compressive strength of some of the hardest known materials in the world, such as granite. And so what we're using this technology to do is to use it for enhanced geothermal rock drilling. So if you're not familiar with drilling technology and drilling, oil and gas is typically found in sandstone-like material, so porous material. But in order to get good geothermal energy, talking about 200 plus degrees centigrade, not what you use for EGS systems, you need to drill through really hard material. So you're thinking about granite, things like chert, etc. And so these materials are really hard, and they damage your drill bits, and they're really hard to drill through. And so your drilling time is really long, which is to drilling operators is cost and money in terms of operator cost, equipment rentals, etc. And so what we're looking to do is use this shock wave to pre-stress the rock, create micro cracks, which make it easier to drill. This project's led by David Stack, who's the plasma expert in our department. We have part of the team, someone working on rock reduction mechanics, and Alan Palazzolo, who is an expert at rotating machines, especially at high temperature and high pressure. Some highlights on the project include an increase in the drilling efficiency. So we see a greater than 50% reduction in the specific energy, specific cutting energy for this technology. And it's rock agnostic, and the best part of the technology is everything is built into the drill string. So there's no wires coming from your from the surface, basically. And so power is generated in situ, and that's part of what I developed for this, or my team developed for this technology. And we can also operate these plasmas and this technology from atmospheric pressure right up to we've done testing right up to about 5,000 to 6,000 PSI. And temperature also is not much of an issue in this particular case. Excuse me. The last project that I want to talk about before we go into thermal transport is the development of some diagnostic techniques for thermal transport applications. And so I'm sure all of you present here on the call know a little bit about plasmas. They are really high energetic ionized gases, for want of a better word, though you can form plasmas in liquids, as I've just shown you. This high energy phase of matter essentially emits light, and that light picked up by a spectrometer can capture the various energy transitions. So you're looking at vibrational, rotational, electronic excitation transitions, as well as in the particular non-thermal plasmas we're working with, there's very high rotational to translational relaxation, which allows us to make the assumption that the rotational temperature is about the same as the translational temperature, which is the way we estimate gas temperature in these systems. And so using the spectra, and matching it to model spectra that was developed out of Stanford, we can do estimates of the plasma temperature. And as you can see, sometimes these plasmas are really high temperature. So at the plasma, the main point in the plasma, the powered electrode in a sense, your temperatures approach 700 plus Kelvin. But what I observed way back when I did my master's was that if you take an unpowered electrode and you put it close to that powered electrode, you tend to develop what you call this very low excitation region, a diffuse glow region near this unpowered electrode. And if you, based on our measurements of temperature near this diffuse glow region, we see that the temperatures are close to room temperature, about 50 to 60 degrees centigrade at the most. When I was doing my postdoc, I got thinking about doing non-contact temperature measurements above the liquid-vapor interface. And so what we're attempting to do in this aspect of this project essentially is to do non-contact temperature measurements above a liquid-vapor interface during evaporation or during condensation. And we have the ability to do it in a spatially discretized manner as well as in a transient manner. We are currently building the test setup for these tests at the moment. Something else that you can do with these plasmas is, because they emit light, and the light that they emit corresponds to the species that's emitting the light, as you can detect the type of species that exists within the plasma. And again, the key here is using these non-thermal plasmas. Now we're looking at doing pulse plasmas in the 10 to 100 nanosecond duration scale. That time scale allows us to operate the plasmas, for example, in water without electrolysis, essentially, and without thermalizing the plasma. And so we do this microplasma induced breakdown spectroscopy, in a sense, breakdown not to the level that you would see in LIBS systems, where you actually damage the material that you're measuring, because the LIBS makes a thermal plasma. Here, your non-thermal plasma is low enough energy that all you see is detection of species. And by counting the photons through a spectrometer and say, for example, a photomultiplier tube, we can actually estimate the concentration of that particular element or molecule or radical in the system that is emitting light. And so the hope is to use this technique for species detection on the order of about 10 to 100 ppm, maybe even better than 10 ppm, depending on the type of spectrometer that you have available to you for measurement of non-condensable gases during phase change heat transfer inside vapors and inside liquids too. So, and that's this is very nascent work. I had a student and he's learning a little bit about plasmas at the moment. So, and this is ongoing simultaneously along with plasma produced water treatment work. Okay, this is the thermal transport community. And so let's talk a little bit more about what we're doing in the area of thermal transport. I'm going to go through the next slide fairly quickly because I'm assuming a lot of us know condensation heat transfer and the different modes. But basically you have film-wise, you add a low surface energy coating to the surface and you can get dropwise condensation. People have been doing this for the last 20, 30 years, where you add surface structures to a simple metal oxide condenser material, and you get these enhanced tubes or enhanced condenser surfaces, which give you this enhanced film-wise condensation mode. You add nanostructures and coatings, and you can get this jumping droplet mode of condensation. But with any sort of coating, you typically cannot condense efficiently with low surface energy materials. And so if you use lubricants plus some lubricant material plus the nanostructures and coatings, you can get dropwise condensation in this LIS slips mode. And of course, the key aspect in all these condensation modes is the coating. and the bulk of the presentation is going to be addressing the durability of that coating. And a small part of our presentation at the end will talk about design of these LIS surfaces, and for the purposes of condensation or anti-icing or anti-fouling behavior, which exists at temperatures outside of the design temperature range. Now, these coatings that we have for dropwise condensation are typically either self-assembled monolayers or they are polymers. In the case of the self-assembled monolayers, which is very widely used in our community to demonstrate dropwise condensation, these coatings fail fairly quickly. The literature says within a few hours, but if you look at the data, it's always within about 30 minutes to less than an hour that these typically silane-SEMs, these fluorosilane-SEMs fail. And while the degradation mechanisms have been proposed to be some level of some type of oxidation, there's no clear indication of what that is. Of course, on the other side, with these low surface energy polymers, you also have similar and different degradation mechanisms. There's the work out of Ninad's group that has looked at one potential mechanism, which is this formation of blisters and delamination. And similar work I've seen out of Evelyn Wang's group at MIT. One aspect that I've not covered here is some of the recent work which has been done out of Simon Dye's group, among others, on a slippery surface that does not involve a liquid lubricant. They're liquid-like materials. But in essence, those surfaces too haven't been tested on a highly on long time scales for durability. So if we summarize, and I've taken this from literature, the different heat transfer enhancements and the timescale over which those heat transfer enhancements have been observed, you'll see that for different types of polymers, whether they're thin or thick, lubricant-infused surfaces, self-assembled monolayers, or these composite structures with metal nanostructures and polymer coatings, you see this wide range over which you can see heat transfer enhancement and robustness. And we started off with these self-assembled monolayers as they are the low-hanging fruit. But as we found out, it's a little more complex than as we always find out when we do research, that things are not as simple as they seem when you start out. And so what we wanted to look at starting out, and what I'm going to talk about in the next few slides, is our work with self-assembled monolayers, looking specifically at fluorosilanes and alkyl silanes. Okay. I like to tell my students every good project has to start out with the hypothesis. And so I present to you our hypothesis here, which was developed by going through not just the thermal transport literature on condensation with silane enhanced surfaces, but we also went through the very extensive literature on from the surface chemistry literature on how people make silanes. What we found as a common thread or trend was that invariably in all the surface chemistry literature, they tended to minimize the amount of water present in the system, because it's well known that these silanes tend to hydrolyze and cross-link in the presence of water, and they don't really form monolayers on the surface, which is a single layer of the coating. They tend to form multi-layers. And so based on that understanding, we said that our hypothesis was that the sources of condensation-mediated degradation are defects. And the defects here we define as uncoated sections of the substrate, which result from the presence of water in the system. And if you think about these silane-coated surfaces in the surface chemistry literature, they say if they make them right, they last for years on end. You can do contact angle measurements or ellipsometry measurements and XPS measurements on them 2-3 years down the line. If they're just sitting in ambient conditions and there's nothing wrong with the surface, it looks as pristine as the day they were made. but we try to understand why during condensation do they fail so quickly. And the idea here is that the process of condensation is different from even doing a contact angle measurement where you have a sessile droplet on the surface. The act of condensation actually creates this potential that drives vapor to the surface. And of course, vapor will be attracted to the locations of high surface energy, which would be these regions that are uncoated on the substrate, because typical metal oxide surfaces are high surface energy materials. So we did two simple experiments. The first one, I'm hoping this video plays. It wasn't playing during the practice run. So, okay, it is. We took a vial of water and we put some silane into the water, and then we waited to see what will happen. And what we observed was, after some time, about less than 5 minutes, you form this silica aerogel in essence. It's this, the silane has basically hydrolyzed and cross-linked in the presence of water, and cross-linked and bonded to itself. And so you form this agglomerate in a sense. This is a fairly large scale process because we wanted to observe it on the macro scale. But we believe something similar happens when you have dissolved water in your solvents during your silane preparation process. And so this is, in essence, this is happening at the nanoscale also on your substrate, which is preventing you from having monolayers, and you tend to have potentially multi-layer coatings. The other aspect is if water is present in the coating environment, the question is, does water have a higher affinity for the substrate than your solvent, which contains your silane molecules? And if water has a higher affinity for the substrate, water is likely to mask the substrate from the solvent, and hence you will again have defect sites where there's no silane bonded to the surface. Again, you need the silane to come in contact with your surface and form the oxane bonds. If it's a silica substrate, it's your siloxane bond. If it's another metal oxide surface, it's a simple oxane bond, which is an SiO and the metal atom, basically. And we observed that in one of the most widely used solvents for deposition of these silanes, which is hexane, we put hexane in a quartz cuvette, so fused silica, and we brought some water in contact with the silica surface, and the water displaced the hexane from the surface. So water had a preferential desire to wet the silica substrate and displace the hexane, which again, we're looking at it at the macro scale, but I want you to picture this behavior happening at the nanoscale, where again, water can mask the surface and prevent bonding of these coating molecules, the silane molecules, to the substrate. The other aspect of the hypothesis is that if you have unfavorable surface chemistry for SAM bonding, you will not form good SAMs on the surface. And this is related to our work with when we transition from silica to other metal oxides. Okay, starting out, we started with the most simple system. We took a double-sided polished silicon wafer, so which has a native oxide on it. And if we had, in an ideal world, which we don't live in, when all the silane molecules line up together, you can have this close packing of the SAM, and you would have this pristine surface with zero contact angle hysteresis and the best coating ever. But in our real world, the best we can do is an anhydrous environment, so no water vapor, no water, dissolved water in the solution, etc. And because of the presence of gauche defects on the tails of the silanes, you can have misorientation of the molecules. They're not all in the same direction. Depending on temperature, the molecules are vibrating around at the molecular scale. And so again, it's possible that you're not always orienting in the right direction. And so you can have some level of defects on the surface. And at the moment, that's the best we can hope for, but we've not really explored this area enough at the molecular scale from a modeling perspective, which is some of the next steps of what we're doing. And finally, in a real environment, or rather an uncontrolled real environment, where you can have water vapor present in the air, water dissolved in the solvent, etc., you will tend to form multi-layers on the surface where you form this, you hydrolyze the silane molecules before they even get to the substrate, and they tend to bond with each other. And so you have multi-layers on the surface, which is what I think a lot of us see in the literature in the thermal transport area. Now, to verify this, we coated these on double-sided polished silicon wafers, and just looking at the AFM scans on the surface, you can clearly see the anhydrous environment, your control environment, where there's no water vapor, has a fairly smooth surface. And if you actually look at the data, you'll see that the anhydrous coated surface after coating has a similar roughness as the original surface, but the ambient environment coating, so something that's in an uncontrolled environment, but we did it with anhydrous solvents to make it even, to give it a leg up in a sense, right, over what is typically done. And it still has a larger roughness, it has a larger thickness, and this thickness is dependent on the time that you have it coating in solution. If you look at the thickness of the controlled environment, the anhydrous environment, you'll see that the thickness is about the length of silane oligomer. And if you look at the contact angle hysteresis again, you'll see that you have this extremely low contact angle hysteresis on the anhydrous coated surface. The next step was to throw it into a test chamber and to actually condense on it. And in fact, we spent a lot of time building this test chamber, not because it's difficult to have 𝗘𝗂𝗃𝗀𝗃𝗃 make you a vacuum chamber, but because we were careful about identifying all potential sources of leaks in the system, and because we wanted to do the experiment in the most pure environment possible. And so we spent a lot of time developing degassing methods, as well as ensuring that there were no non-condensables in the system when we were operating. Because if there are non-condensables in the system when you're operating, then our hypothesis is we may not be able to come up with the right hypothesis, because we have potential for air interacting with the silane also, which adds an additional variable in the system, which we don't want. And then we put the silicon coated samples in the system. We did 4 sets of runs in the sense that we have an anhydrous environment coating with an alkyl silane and a fluorosilane. And then we have the ambient or uncontrolled environment with a fluorosilane and alkyl silane too. And what we noticed that was right up to about 150 hours, there's no change in behavior on these surfaces. And we expect that because silanes will bond well with silicon. But as we progress through the experiment and we get to this point of about 450 plus hours, we start to see that the ambient environment coatings start to fail. And they fail more so on this fluorosilane surface. But if you compare that to the anhydrous environment coating, you'll see little to no degradation on the surface over time, over this entire 450 plus hour testing period. We had to stop the experiments at 460 hours because we wanted to actually see what is happening with the surfaces that failed. And my student wanted to graduate, so a lot of stopping experiments is to not obtain binary data, as well as have data available in a time frame that's conducive to a 3 or 4 year PhD degree. So, but if you look at the XPS data that we see, that we obtained before and after the testing process, you'll see that the longer tail silanes actually performed better. In this case, the alkyl silane, even though the fluorosilane has better wettability properties that you would want. It has a slightly higher advancing angle and a slightly smaller contact angle hysteresis compared to the alkyl silane. The alkyl silane actually had better performance in terms of degradation or durability after condensation. And so aspects that we observed in the fluorosilane was that in the ambient environment, so the uncontrolled environment, you completely lost all the fluorosilane from the surface in the regions that you can see as film-wise condensation. And in the anhydrous environment coating, you tended to lose some of your silane molecules, but not a lot of it. The next step was to move to metal oxide surfaces that are more common in heat exchangers. And so we picked copper as a starting point. But silane bonding to these metal oxides is a little more complicated. It's not as straightforward as forming that siloxane bond. And so we had to tweak a little bit the surface chemistry. And after trying a bunch of different aspects, one of which we've not really tested as yet, but we ended up on pure oxygen plasma treatments. If there was any air, so nitrogen or some of the other components of air present in the system, the coatings weren't as good as a pure oxygen plasma. So we had to do multiple purges of the plasma treatment chamber in order to achieve that pure oxygen environment for the plasma treatment. The one aspect that we've not yet tried, but I do want to try, is using an oxygen and water vapor plasma. And so in order to create the right chemistry to get the best surface bonding on the surface. And that's something is going to happen in the next 6 months or so. Okay, so we tested 4 different types of samples. The topmost row is what typically exists in our community. So almost everyone I know, oxygen plasma treats the surface and then does coating in an ambient environment. We also did no plasma treatment and coating in an ambient environment. And then we did the anhydrous environment coatings with and without oxygen plasma treatment. And the top row demonstrates exactly what people see in the literature. It starts out at dropwise condensation, and then within 20 minutes to half an hour, it starts to fail. Within 2 hours, it's all gone. And the no plasma ambient environment coating has no chance. Absolutely, it fails even faster than the plasma treated surface. What we did observe was the anhydrous coating environment, even without a plasma, seemed to do fairly well right up to about 24 hours, after which the coating started to fail. Sorry, was there a question? Okay. And the oxygen plasma in the anhydrous environment actually performed fairly well right up to when we stopped the experiment at about 360 hours. And so we clearly see the benefits of the right surface chemistry, as well as minimizing the amount of water present in the coating environment. Something interesting that we observed, and we've still not been able to explain it because my student has graduated and the new students getting trained on all the different methods, as well as working on some of the plasma work where some of the new funding is. And so, but this behavior that we see, where we see this change in color of the surface as a function of time, is fairly interesting. And we believe that there's some electrochemical aspects to it that we are currently attempting to probe. But as I'll talk about in the next slide, I think it's some level of a chemical reaction that's changing the oxide nature on just below the silane coating. And if you look at the XPS data, it actually shows you that we are transitioning pre-condensation from a completely copper oxide surface to this cuprous, from a cupric oxide surface to a cuprous oxide surface. And we believe this cuprous oxide surface is more soluble than the cupric oxide, though there's not a lot of evidence either way in the chemistry literature on which the solubility of one versus the other. We do have this hypothesis for what our mechanism of degradation is, and that is once you have a defect site, you preferentially start to accumulate water in that area. And as water sheds from the surface, the droplets shed from the surface, you bring fresh water to the surface. Keep in mind, the condensate that is formed is deionized water, right? And deionized water is highly reactive. And so you will tend to eat away at the oxide on the surface. As you eat away the oxide, you're basically removing the coating from the surface because the coating is bonded to that oxide. And so a very simplistic view at what that mechanism is, you have defects, and irrespective of the substrate, the end result is dissolution of the oxane bond, whether it's a siloxane bond, SiO-Si, or a CuO-Si bond with the copper surface requiring an additional reduction reaction, likely from CuO to Cu2O. Now, that's a lot of surface chemistry. We also did some heat transfer measurements, again in the same chamber, but this time we coated some copper tubes. And to validate our test setup and our measurements, we compared it to the literature. We get little similar or little better results than what's existing in literature. And these are fairly well-cited papers. And so we said, okay, the experiments are good. In terms of dropwise condensation, let's look at what our heat flux behavior is like. And so a typical experiment, for those of you who do condensation work, is we start at the lowest subcooling and we increase subcooling right up to the point where the system cannot maintain steady state anymore. And so we collect the heat flux data as a function of the subcooling. What you'll observe in the plot on the left is 2 data points that are in pink compared to the rest. And those data points were actually taken after we finished the entire experiment. So the experiment lasted about 4.5 to 5 hours on average. So we stepped up the subcooling, collected the heat flux data. And after the entire experiment ended, we went back and reduced the subcooling and collected data again at one of the low subcoolings. This tells us 2 things. One is our system is fairly clean in terms of presence of non-condensables. So in that 4 or 5 hours, we did not accumulate sufficient amount of non-condensables to affect the experiment. And this is important because even 1 or 2 Pascal of non-condensables can really affect condensation performance. The other thing it told us was if the performance is the same before, at the start and at the end, most likely the coating itself has not failed. And so it validates this approach to doing coatings in this anhydrous environment and with this oxygen plasma chemistry. You see this again with the heat transfer coefficient measurements. Not too happy with the scale bars. They are rather not scale bars, the uncertainty bars. This method is not the most conducive to getting the high sensitivity to the heat transfer coefficient, and so that's another avenue that we're looking to improve upon. But in general, we see very considerably higher heat transfer coefficient enhancements over the film-wise mode. We did the experiment, like I said, over about 4.5 hours. All the data was collected right up to about 2.5 hours, and then we just ran the test for another 2 hours to look at the change in heat transfer coefficient over time. And as you can see from the data here, there is almost no change in the heat transfer coefficient within the uncertainty. Again, the uncertainty is pretty high. But if you look qualitatively at the droplet departure sizes, there is not much of a difference between the start and end of the experiment. And so it tells us again that not sure why this video is not looping, but it tells us that the coating has not been damaged too badly during this time, or nothing that can be measured in the timescale that we tested them so far. Okay, one last pivot, not too far, but I'm going to switch gears a little bit to talk about the design of these lubricant-infused surfaces for condensation. So you recognize this video from before. You have this hexane pool sitting in a quartz fused silica cuvette. We put this droplet near the quartz surface, and the water droplet displaces the hexane from the surface, which indicates that, which is somewhat counterintuitive. Hexane has a lower surface energy or surface tension than water. You would likely predict it to want to stick to silica and reduce the silica surface energy further. But water seems to have an affinity for the silica surface. And so, as my good friend Dan Preston, who's on this call, I believe, showed a few years back, the interactions between water, which is the polar molecule, and silica, which has some polar behavior, make silica want to preferentially bond to polar molecules, even in the presence of a substance that is lower surface energy. And so this comes about from a theory called surface tension components, where you split up the surface tension or surface energy of a material into its apolar and polar constituents. And this is one particular framework that's used to design lubricant-infused surfaces for whether it's anti-fouling, anti-icing, or even condensers. But a lot of the design happens with data that's only available at either 20 or 25 degrees C. It's not really consistent either. But as you can see from condensation experiments, they operate anywhere between 65 degrees C for air-cooled condensers right down to close to 0 degrees C for anti-icing applications. And the question is, how do you predict behavior for this wide range of temperature, given that surface tension and interfacial tension change fairly or a good amount over that temperature range? And so the goals of this ACS-funded project were to develop this database of temperature-dependent component data, surface tension component data, and validate / I've not written here, but invalidate the model framework, as we are pretty agnostic to what works. We just want to know if it works and does it work over a temperature range. To give you a brief overview of what this surface tension component framework looks like, you can split up the surface tension of a fluid into its dispersion or apolar component, which is this superscript LW, and its polar component. The polar component further has this combining rule that combines the Lewis acid component and the Lewis base component. And so those are the apolar and polar terms. When you have two fluids interacting, fluid 1 and fluid 2, you have this larger expression that explains the interfacial interactions. But if fluid 1 is polar, like water, and fluid 2 is completely nonpolar, like hexane, the non-polar fluid has no polar components, and so your equation reduces down to something that's fairly easy to test. You basically have one equation, one unknown, and because the interfacial tension is something that you can measure. Now, again, we started out with this hypothesis that the relative polarity of water does not change in this temperature range. And if our hypothesis is true and the framework is accurate, the measurements between water and a truly nonpolar fluid should match up in this model framework. And to do these experiments, we had my student developed this or put together this test setup to do very controlled measurements of surface tension and interfacial tension using the pendant droplet method. I've got to give her a shout out. 𝗘𝗂𝗶𝗀𝗃 really has done some of the cleanest measurements I have seen for surface tension and interfacial tension over a fairly wide temperature range. Again, that's maybe my bias because she's my student, but I think she's done some really great work. This is what the setup looks like. And let's take a look at some of the data. So we first validated our method, our measurements with the literature. Literature is shown in the shaded symbols, and our measurements are in the open or unshaded symbols. We have fairly good agreement between our measurements and the literature for a wide range of fluids. We picked some truly nonpolar fluids like linear alkanes and the cycloalkane and a perfluorocarbon. We have water, which is a fairly polar fluid, or the most polar fluid in the chemistry literature. And we have some fluids that are slightly in between. They're considered to be nonpolar from the perspective of the surface tension component theory, but as we have seen in our data, and this manuscript should be submitted before the end of the year, so hopefully you'll see the data soon. We have some conflicting results from that. But what does work well is that because these linear alkanes are known to have really low relative polarity, the model and the experiment match up fairly well within this assumption, with the assumption that the surface tension component for the dispersion component for water is fairly constant over this temperature range between about 20 or 25 and 65 degrees C. And in fact, it is about 30% of the total surface tension of water for these temperatures. So with this validation of this framework for water with really nonpolar fluids, we want to perform some experiments, condensation experiments, and see whether this actually is true during condensation. Of course, we'll apply some other design tools, including some of the work done by Paddy and Anad in this space. With regards to the coding work, we still have to identify the extent of durability. 460, 500 hours doesn't cut it for industrial applications where they want tens of thousands of hours or 10,000 to 15,000 hours of durability. And that's some aspect that we're currently working on. The electrochemical behavior is another aspect that we've just begun to look at. And we have some collaborative work with some experts on reactive molecular dynamics to look at some of this behavior from a molecular scale. And finally, we are developing these plasma-based diagnostics for non-condensable gas concentration measurements in both liquids and vapors. But that's more at the experiment design stage. And hopefully in a year or so, we'll have some data to show, preliminary data to show on that. As always, I've got to acknowledge my students. They're the ones who do all the work, my collaborators, and our funding sources, without whom we would not be able to do what we do. A special thanks to ACS, PRF, the Energy Efficiency and Renewable Energy Office at the Department of Energy, ARPA-E, NSF, and some seed funding from the university as well as the College of Engineering. Thank you very much, and I'm happy to answer any questions that you may have.
Thank you, Dion, for this excellent talk. If anyone has any questions, feel free to turn on your microphone and directly ask questions, or you can post your question in the chat. I saw Patty already raised her hand. Patty?
No, I was just applauding for a great work and
gotcha.
Great presentation.
I have a question, if nobody else does.
Oh, yes, Nana, always.
Hey, Dion.
Hey.
Thanks a lot for the great talk, man. That was great. I didn't know you were doing so much fantastic work. Just to give you context, I'm actually calling in from Hawaii from a family vacation. So
oh, lucky.
And I'm glad I saw it. I just had a comment, less of a question, but a comment on the SAM degradation work, especially the cuprous oxide slides. Have you guys done anything with analysis of the condensate itself? And
no,
the reason
okay, please go ahead.
Yeah, I was just going to say, if you collect the condensate, you could do things like EES or GCMS to actually see copper content inside the liquid itself. So maybe you're already thinking about that, but it's just more of a comment.
We haven't tried that as yet. We didn't think about that for the, but we should. The reason we didn't think about that was we didn't really see any drastic residue of copper inside the chamber after we ran the experiments. But it's something to, because we dry the chamber out, but it is definitely something that is interesting and we should try. We have everything up and running. So
right, like DI water will definitely take on, it'll definitely take on copper ions, and that's actually one way copper is antibacterial, because the water will solvate the copper ion, and then that'll interact with bacteria that's in the water. So that's why classically people like to use copper as a material, right? As compatible and safe. And we have done things with EES in the past, not for condenser applications, but for actually bacterial work. So it's something you may want to think about, just in terms of characterizing differences, like on one SAM coating versus the other. And although I'm not sure it'll pick up things like oxygen, But that can be
But we
oxide.
should be able to see the copper in that. So
Yeah, it'll definitely give you copper signals and copper quantities, and so
yeah.
Yeah. Other than that, great work, man. I'm glad I called in.
Thank you, and enjoy your vacation.
Oh, I will. I will.
And I have a question if no one else does.
Sure.
So you mentioned non-condensable gases multiple times, right? And I understand that obviously if you have non-condensable gases, the transfer coefficient will be limited by the accumulation of non-condensables at the interface. But when I think about commercial condensers, though, you always have some degree of contamination, and so the question is whether you have plans or you already investigated the effect of dropwise condensation and maybe even jumping droplets on the heat transfer coefficient with non-condensable gas.
There's a lot of literature on the dropwise condensation with non-condensable gases, and so that's not something we've looked at ourselves. The reason we wanted to minimize non-condensable gases was because we wanted to eliminate any potential extra aspects that could affect performance or could affect our mechanism. So we wanted to eliminate, we wanted to have a control experiment, right? We wanted to eliminate anything that could affect it in order to prove or disprove what we thought was the hypothesis. Now, in terms of heat transfer coefficient, I believe that there's a lot of work from the 60s or 70s that was done with non-condensables. But we are working with non-condensables and some of the jumping droplet work. That's some ongoing work that we have. Though, again, the key issue what triggered what we are thinking about with non-condensables was the only way we can measure non-condensable concentrations is with the pressure transducer. And if you do the math on that, the limit of what you can measure, your least count, in a sense, of your measurement is about 3,000 to 5,000 ppm. And if you look at the models that are developed by John Rose for how non-condensables can affect heat transfer coefficient, he talks about data below 1,000 ppm, according to the models that can affect performance. The only way to verify that is to be able to measure NCG levels at that hundreds of ppm level. And that's where the idea for using these plasmas to do the measurements came about. And so this is simultaneous work that's going on where we are looking at non-condensable measurements with the plasmas, along with some of the effect of heat transfer coefficient with non-condensables and jumping droplet condensation. Though there is some work that's been done in the literature with jumping droplet condensation and non-condensables. Not directly, that was not the intention. It just happened in the work. I think that's the work by Rongwei Yang's group in Joule, I think so, if I remember correctly, where they had high concentrations of non-condensable gases, but the jumping droplet heat transfer performance was better than film-wise in the presence of the NCGs still.
Thank you, Dion.
Thanks.
Thank you, Dion. May I have two questions regarding your earlier slides?
Sure, please go ahead.
So you have slides showing the plasma-based vapor temperature measurements.
Yeah. Do you want me to share the screen again?
Yes, that would be great.
Sure. Let me just pull that up. But go ahead, I'm listening.
So I'm just wondering what would be the spatial temporal resolution and also the fluctuations, like uncertainties.
Yeah, so that's the one aspect. Uncertainty is the major issue with such a measurement. Uncertainty depends on the quality of your spectrometer and the CCD that you have available to you. Uncertainty can be down to about plus or minus 5 Kelvin with a good spectrometer that has a really super high resolution with the information that we have available to us. Uncertainty with the spectrometer that I have is probably around plus or minus 30 to 50 Kelvin. which is not really that good, honestly, right? But the hope is to identify as a concept whether this is even possible. Now, with regards to spatial resolution, that really depends on your CCD. And in terms of temporal resolution, again, it depends on your CCD. You have these picosecond gated CCDs, ICCDs, or EM ICCDs, whatever, that can go down to really low time scales. But unless we're doing the measurements with ultra fast plasmas, I don't see the need to go to that high temporal resolution, given that we don't expect heat transfer processes to occur. At least I don't, and I could be wrong, to occur at this nanosecond or picosecond timescales. And so, yeah, it depends on the equipment you have available to you. Let me put it that way.
So does that mean with this approach, it's promising to get a thermograph instead of just a single point measurement?
Yes, yes. It is possible to get a 2D measurement, a map, in a sense, right?
Or even 3D?
If you put enough cameras and enough spectrometers, sure.
This is very impressive. Thank you. Another question is,
the uncertainty is something that you have to work on, right?
Follow up on that. How do you calibrate it? How do you calibrate it?
And so calibration of, sorry about the coughing again, as we were discussing earlier, kids. Calibration of the temperature is, it only depends on how good the models are available to you. And these models are fairly good that came out of the Stanford work. The group is called 𝗑𝗫𝗫, or the company is called 𝗑𝗫𝗫. For the calibration for the species detection concentrations, that depends on how good you can calibrate your system, in whether it's the concentrations you can control in your system, etc. And in terms of the counts, these photomultiplier tubes are pretty good, so I don't anticipate that being the limitation. I would say your calibration is going to be a limitation in such a system. Sounds
great. Another question is about your Ascend project. In that project, you show the co-design of the electrical system and the heat exchanger. I'm just wondering whether any of those fancy science you talk about later are implemented in this more like an application-driven technology.
I would like to have used two-phase work in this project, but 𝗘𝗏𝗃𝗃 is very risk averse. They say they are they're excited about risk, but they want us to de-risk everything. And I think because this is an aviation application, they wanted to de-risk it even further. And so they are leaning on us to do single phase for the heat sinks, and that's why we call it the air heat exchanger here. But we are, as a team, we are looking at two-phase flow on the side, since we have the capabilities. The one aspect that the one important aspect of co-design is the design of the heat sinks themselves, because the heat sinks are made out of metal and their heat sinks are directly mounted onto the windings. You can have EM losses that are eddy current losses that are generated due to the metal and conductive nature of the heat sinks themselves. And so designing the heat sink, there is some IP for us there. And so that's some of the interesting part for me in terms of the intellectual aspects of the work. But from a thermal transport aspect, it's pretty, it's exciting that we have the work and we can try new things, but I'm not using state-of-the-art two-phase techniques personally. So,
got it. Thank you.
And I think we are right in time.
Yeah, we have one last question in the chat. Ato, do you want to read your question to Dion and the audience?
Yeah, hi. Thank you once again. I mean,
hello, Atul.
Okay. Hi. So this is Atul Srivastava from IIT Bombay, India. I was just wondering regarding your non-contact temperature measurement technique. I mean, would it be possible to have the simultaneous measurement of vapor concentration as well as the temperature through the approach that you have discussed? or is it only restricted to single scalar measurement?
No, I think it's possible to have them happen simultaneously. The key with the temperature, and that's, okay, let me put it this way. You want them to happen simultaneously when you have okay, I'll say no, because of the timescales mainly. Okay, the temperature measurement requires you to probably be operating with pulses on the order of about milliseconds, tens of milliseconds. Whereas the species detection, you probably want to operate at much lower timescales, just because of what it can do to the system. And if you're in the vapor phase, then sure, tens of milliseconds will work even, and then you can do simultaneous measurements. But if you're in the liquid phase, I would not want to do long-term pulses because of the potential to do basically electrolysis of the fluid, right? Because you're typically working with conductive fluids in that sense.
So you mean to say this is limited by your kind of this temporal resolutions that can be offered? Is that the limiting factor for this?
It is the limiting factor because when you're in the liquid phase, you do not want to alter the fluid much, and so you're going to be operating in this sub 100 nanosecond pulse range.
Sure.
If you're in the vapor phase, you have a little more leeway of how long you can have your pulses.
Sure. All right. Yeah.
That answer your question, Atul?
Yeah. Thanks a lot. Yeah, I'm done.
You're welcome. Happy
All
to
right.
have conversations offline. Shoot me an email, please.
Sure.
All right. Thanks, Dion, for the excellent talk. Thank you, everyone, for attending this session.